Okay, here we go with a little ultrasound application. Whiteboard problem 16.6. So we have velocity of blood flow in the aorta is normally 0.32 meters per second. What beat frequency would you expect if a 5.5 megahertz ultrasound waves were directed along the flow and reflected from the blood cells? Assume the waves travel with speed of 1.54 times 10 to the 3 meters per second. Okay, here we go. So there's actually two steps to this problem. So this is the velocity of the red blood cells. And then we have the velocity of sound through that medium is 1.54 times 10 to the 3 meters per second. So we're given. And then the emitted frequency is 5.5 megahertz. And we want to find the reflected frequency, or detected, I guess, by the ultrasound. Right, so you have it's sending out waves, and something's coming back, and it also detects them, and it actually looks for measures the beats, right, or the shift between those two waves. So two things are happening here. So let's assume the ultrasound's not moving, right? But let's say that the red blood cells are moving away from the ultrasound in this case. So the red blood cells actually hear a frequency that's a little bit lower than what's emitted because they are moving away, right? And then, so they're going to reflect that lower frequency back to the ultrasound, but the ultrasound is going to hear an even lower frequency because it sounds like the lower frequency was emitted by a source that's moving away. So there's actually two different shifts in there. So let's do it in two stages. So I'm going to say part one, what does a red blood cell hear? So in this case, we have an observer moving away. Okay, so we have the ultrasound staying still, my observer. We can make it this first red blood cells moving away with some speed blood cell. Okay, so our Doppler shift formula tells me that my observed frequency is my emitted frequency. And then I have the speed of sound plus minus the speed of the observer, speed of the sound minus plus the speed of the source. Okay, so in this first part, my source is not moving, but my observer is, right? Because we're saying, what does the red blood cell hear if the red blood cell had ears? Okay, so that's 0. Okay, and then we know that our red blood cell is going to hear a lower frequency because it's kind of outrunning the waves. So we want this to be negative, right? Because we want this fraction to be less than 1. So the frequency observed by the red blood cell is going to be our emitted frequency times the speed of sound minus the speed of the blood cell divided by the speed of sound. Okay, so that's the first part. Optimize there. Okay, and then part 2. What does the ultrasound want here? So, this is connected to some wand here, right? So it's emitting, but then also going to listen for the echo. Okay, so in this case, it sounds like a source moving away. Sorry, this is like the 6th one. I can't think anymore. Where really where the emitted source kind of is, or the emitted frequency is going to be what we just calculated, what's observed by the red blood cell. Okay, so again, we go to our Doppler shift equation. So the observed frequency is the emitted frequency. v minus or plus minus the observer, v minus plus the source. Okay, so now we're thinking about this guy listening to the reflected wave. Okay, so in this case, the observer is not moving. That goes to 0. But now the source is moving away with the speed of the blood cell. Oops, move that down a little bit. So it's F emitted, we'll talk about that in a second, and then it's the speed of sound, which we have up here. And then we have, again, we want this to be lower, so we want the plus on the bottom, V plus the speed of the source, which is the speed of the blood cell. Okay, so this is observed by the ultrasound. Or I guess we call that F detect. Detects, okay. And now we want to take, for what's emitted by the blood cell is what's heard by the blood cell up here. So the detected frequency equals the emitted frequency of the ultrasound, V minus V blood cell over V, and then times this, right? So that's here. And then we have the shift that's due to the ultrasound detecting a reflected wave from a receding source, V plus V blood cell. So these V's go away. So we get our emitted frequency, V minus V blood cell, V plus V blood cell equals our detected. Okay, so let's turn to, so this is going to be our emitted, right, is 5.5 megahertz. Our speed of sound in the body, 1.54 times 10 to the 3 meters per second. The blood cell, 0.32 meters per second. And then 1.54 times 10 to the 3 meters per second plus 0.32 meters per second. Let's see what we get. Okay, so we get 5.5 megahertz. We'll just say our emitted frequency is 5.5 times 10 to the 6 for megahertz. Our speed of sound is 1.54 times 10 to the 3. Speed of the source observer is 0.32 meters per second. So then our observed frequency equals our emitted frequency times the speed of sound minus the speed of the observer divided by the speed of sound plus the speed of the observer. So that's what we get. And then if we want to know the shift, we would take the difference. F emitted minus F observed. Okay, so our shift, delta frequency is, so here we'll put this down. Our detected frequency is very similar to the 5497714 hertz. That's kind of writing them out there. And our shifted frequency is 2285 hertz. Okay, that's it for chapter 16. Thank goodness.